Hey everybody, it's Mr. Molikash again. Get ready for week 3 of Calculus 1. This video is primarily intended for students at Johnston Community College, where I teach Calculus 1 and other courses, but hopefully if you found this on YouTube, you'll find it helpful as well. So without any further ado, I want to get into kind of what I wanted to cover in this video. The first thing is in my last video, there's a conundrum about vertical asymptotes and something called the sign chart that created some confusion. I'm going to be really lenient for those of you that were a little confused on that with your last lab assignment. And I'll talk about that here in a few minutes. Also, kind of want to recall continuity and the intermediate value value theorem from the last video. So if you haven't looked at that in a while, you're definitely going to want to check that out, right? You're going to want to know how a function is defined to be continuous, and what the intermediate value theorem says. Especially, please pay attention to the fact that on a given interval, a function must be continuous. That is really important. That's going to come up in this week's lab, okay? The intermediate value theorem does not apply if a function is not continuous on a given interval. Okay, you cannot, the theorem doesn't guarantee anything, okay? All right, and we'll talk about the squeeze theorem and what it means to have instantaneous velocity. We've been hinting at the fact that, the slope of a line between 2 points can sort of approximate the slope of the tangent line at one point. We've been talking a lot about this tangent line business, and so we're going to start putting some meat on those bones. And in particular, how it relates to this thing called instantaneous velocity. And that leads us to the limit definition of the derivative. So if you remember my first video when I gave you this outline about what calculus is, and how there's these different branches, there's derivatives, there's integrals, we're going to start unpacking what the derivative is at the end of this video. And then finally, this week is where you get to start using Maple. Okay, so at the end, I'll show you how to download Maple, and if you're a JCC student, what code you get to use to do that. Okay. All right, great. So to start with, the VA or vertical asymptote thing, right? Let's say that we have a function. And the function is a rational function, 1 over x minus 3 squared. And we want to evaluate the limit as x approaches 3 of this function. Okay, so the business of sign charts and all this kind of stuff, I don't know that I did the greatest job explaining this, but I'll try my best to kind of flush this out for you guys. So if you have x values on either side of 3, so 3 is sort of our focus, right? We're going to try to head toward 3, and because this is a two-sided limit, we're going to head toward 3 from values smaller than 3 and also from values larger than 3. And so we're going to input some values and for x that are approaching 3, and then on, like I said, on either side. Okay, so maybe a really close number is 3.0. Oops. Let's put that on the right side. That's definitely greater, isn't it? So early in the video, and I've already made my first mistake. Okay, hopefully you'll forgive me for that. So let's say that's 2.99. So these numbers are very, very close to 3, right? But we'll get some other numbers that aren't so close to 3, like 2.9, 2.5, and maybe just 2, right? And over here we'll do the same thing. This will be slightly further away, so this will be 3.1, 3.5, and 4. Okay, and I don't know about you, but the way that I do this, like in a hurry, like really quickly, is to just use a spreadsheet. So I'm going to show you real quick how to do that. I'm going to pull up my spreadsheet, and I'm going to start a new spreadsheet, and I'll put that over here on the left side of my screen. Now, hopefully everything is big enough where you'll see this. So I'm going to put x's on one column and f of x's in the other. And hold on just a second. I'll make this all big enough to where you can see the text, hopefully. Okay. All right. And so we'll just start copying numbers here. Let's see. 2, 2.5, 2.9. And I'm going to use a spreadsheet formula to do this because I'm lazy and I don't want to keep plugging numbers into my calculator. Okay, and it's fine for you to do this too. You can generate this table however you want. So what we want to do is we want to do equals 1 divided by parentheses. Now our x value is located in cell B1, so we're going to do B1 minus 3 close parentheses squared. Okay, and so when I do that, I get the value 1, right? Now I'm not going to write all these numbers in because you're going to be able to see them here in my spreadsheet, but what I'm going to do is just take this cell here and see the lower right hand corner of this particular cell has a little tiny box, and you see what you can do is you can take that and you can click and drag and fill that cell to the right, and you'll see that in the middle we have a problem, right? It says division by 0, so obviously f of 3 in this particular function is undefined, right? Let me write that down. So f of 3 is no bueno, right? It's not a number. Whoops. I hit that button again. I tried to get some practice in this week so that I wouldn't do that so much like I did last time, and I'm still doing it. So y'all just kind of help show me some grace here. I'm trying not to hit that certain button on my stylus where that happens. Anyway, f of 3 is undefined. Okay, so there's nothing there, but we have some other numbers, right? And over here, like, okay, the y values on x values less than 3 are getting really big. In fact, they're all positive, right? But they're super positive. They're super positive. I would say like really, really big, right? And the same thing over here, right? It's actually, this is an even function and across the line x equals 3. So all these are positive as well. And so what I think a previous instructor may have meant when they wrote that problem was that there's positive numbers on either side. So what we expect for this to be is a positive something, right? Now, the sign in and of itself doesn't tell the entire story. What tells the story is the magnitude or the size of these numbers. That's what I was trying to get across in my announcement earlier. So it turns out that those numbers get, like if you were to split the difference here and do 3.001, it would be an even bigger number. It would be like 100,000. So as we are approaching, the y values on the left and the right side are getting so big, we're going to say that this is positive infinity. And when, oops, there I go again. I really need to watch where I put my fingers on this thing. Okay, positive infinity, and when this happens, we say that this function has a vertical asymptote at the line, the vertical line, x equals 3. In fact, we can show you that real quickly. So this table kind of gives evidence, and I think the table tells more of the story than just the sign of the number. So I wasn't too big of a fan of you just doing a sign chart, even though that's what was written in the directions. So, you know, if we were to do in Desmos calculator, right, if you were to graph this function, you know, f of x equals, you would definitely see what's going on, right? Graphically, across the line x equals 3, values on the left side are getting really big, positively big, right? And on the right side, they're also getting positively big. So on each side, the one-sided limits are both approaching positive infinity. And I tend to think of these problems more graphically than I do numerically, but it's important to kind of see them both ways, right? To see the numerical data as well as the graph. Okay, so that's a little bit on that. The next order of business is to review continuity for this week's lab. I talked about this in last week's video, but just remember a function f of x is continuous at x equals c if and only if three conditions apply. What are the three conditions? If you don't remember, I'll tell you what they are. First off, f of c has to be defined. F of c exists. So, you know, that earlier problem that I had on there, the f of 3 didn't exist. Not continuous. Obviously, there was a vertical asymptote. Okay. A second condition that has to apply is the fact that the limit, the two-sided limit, as x approaches this c number of f of x also exists. Okay, so there has to be a limiting value as we approach x equals c. Y has to approach something from either side, and the same something from either side, right? And then the third thing is that these two things both have to be the same number, right? So the y value that we get when we plug in x equals c has to be the same thing as the limiting value. Okay, so if you want, all three of these conditions have to apply. So if you want more information on this, check out my earlier video on continuity and the intermediate value theorem. You can search on YouTube, or if you're one of my Blackboard students in JCC, just look in week 2. Okay. Next order of business is to review the intermediate value theorem, or IVT it's sometimes called, intermediate value theorem. And just a real quick recap of that, if a function f of x is continuous on a closed interval from a to b, then there must be at least one value. There could be more than one. C, where C is strictly between A and B, and f of c is strictly between f of a and f of b. And there's a picture that kind of goes along with that, right? So let's just quickly draw that. Let's say that there's an a and there's a b, and this is the origin right there. And so we'll let this be our f of a, and this be our f of b, and we'll draw some point here. So yeah, something like this. Okay, there we go. So there is the point b f of b, and there's the point a f of a. So there, you pick a y value. Pick a y value anywhere in the interval here. This one. There's an f of c. All right. If you pick a y value, there's got to be at least one point interior to the interval between A and B that obtains that y value. In fact, there's a whole bunch of them here, right? There's C1, C2, C3. See what I'm talking about? Ha 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 ha. Okay, so as long as the function's continuous, we're good. If the function is a break in it, if it's vertical asymptote, if there's a hole in the graph, whether it's removable or non-removable, this theorem does not apply. So keep that in mind, because that's going to be an issue for you, my students, on this week's lab. Okay. All right. Moving on up the chain. Our next order of business is this thing called the Squeeze Theorem. And so what I thought I'd do, instead of showing you the textbook this week, is I would show you a Wikipedia page. There's a Wikipedia page on the Squeeze Theorem, and there's a real good statement about this thing called the Squeeze Theorem. It's formally stated as follows: let I be an interval having the point A as a limit point. There's a lot to what a limit point is in higher level mathematics, namely topology and stuff like that. I don't want to go into all that, but let G, F, and H be functions defined on the interval, except possibly at this one point. Okay, so just keep that in mind. Suppose that for every x in the interval not equal to A, we have f of x is sort of squeezed between g of x and h of x. So we find two functions. One is called a lower bound. G is called the lower bound because it's underneath the function. H is called an upper bound because it's above the function. And if we can squeeze a function in between these two, and the two outer functions, the boundaries, have a limit at x as x approaches A, then the function that's squeezed between them must have the same limit. Okay, so what the heck does that mean in practice? Let me go through an example with you. Okay, let me go through an example with you. So let's say that we wanted to evaluate a limit, right? Let's say we want the limit as x approaches 0 of the sine of x divided by x. Okay, now you can't just plug in 0 into this, because if you remember, the sine of 0 is 0, and you definitely can't divide by 0, is nothing, right? So this is the A that they're talking about, right? This function f is defined, but not defined at 0, right? So the limiting value is 0. The limit point 0 is just not there, right? There may be a hole in the graph at this function. There may be an asymptote. There may be a broken discontinuity or non-removable discontinuity. We don't know. But the way that we're going to evaluate this limit is by squeezing this between functions, and we have to look at a graph to do this, and later we're going to use Maple to do this kind of thing. So what I have done, so we definitely can't plug in 0, no bueno, right? Can't do that. But what I have done is I graphed this function. If you were paying attention earlier on the left side, I graphed this function, and it sort of looks like a sine graph, especially near the origin. But then it kind of flattens out, right? The more you divide it, the bigger the number you divide it by, the smaller it gets, right? And so I happen to know that this middle point, this middle area right here, let's say between -1 and 1, it kind of looks like a parabola. I'm going to draw a parabola over this. It kind of looks like a parabola. And if you know something about your parent functions from Math 171 and how to transform those, the parabola that is flipped over, that is flipped upside down, is this, and then that parabola is moved up 1 unit, right? So that would be negative x squared plus 1, or just 1 minus x squared, right? I could just say that. All right, so for all intents and purposes, this is going to be our g of x. We're going to let g of x be this lower function that kind of like squeezes the graph. It's very close to the graph but the red graph is always greater than this or equal to it. Okay. Now, we're also going to give this graph an upper bound. And an upper bound, super easy upper bound for this is anything that's above it. So I'm just going to let that be y equals 1. Or rather, h of x equals 1. Okay, so I'm going to graph these in Desmos instead of writing this on here. And I wish I kind of had a bigger eraser, but just be patient with me. All right, and yeah, I'm going to graph these in Desmos. So here we go. Maybe. Hey, there we go. So I'm going to call g of x, my keyboard will cooperate with me, 1 minus x squared. Okay, and let's change the color of that. Let's change that to a blue. All right, so the blue graph is always less than this red graph. Okay, so over here I'd like to say that we're going to have the statement from the squeeze theorem is that we must have a g of x and an h of x that are boundary functions for this f of x thing, right? Now, I forget about the, I think, yeah, it's less than or equal to, it could possibly be equal to, except at the limit point, right? So this is true, except at x equals 0, okay? So you could pick any interval, and I'll pick the interval, say, from -1 to 1, okay? Definitely 1 minus x squared is less than or equal to this crazy function sine of x over x. All right, so yeah, that is definitely happening. You can see that, and hopefully you're convinced of it. And then y equals 1, let's go ahead and put that over there, or h of x rather, equals 1. And what do you know, they made that the same color too. Let's make that one green, and this is called an upper bound, right? This is called an upper bound. So 1 is greater than all the red points except possibly at 0, right? Except possibly at 0. Okay. Now, because this is true, and we'll pick, we'll say on the closed interval -1 to 1 that this is true, right? So we can easily find the limit as x approaches 0 of the lower bound, right? You know that the polynomial is continuous for all real numbers. There's no breaks in the graph or anything, so because of that, we can just plug in 0 and we get 1, right? Okay, so we know that. We also can do the limit as x approaches 0 of our upper bound function. That's pretty easy to do, right? It's 1. So because this inequality is true, and because these limits exist, then we can conclude, therefore, that's what those 3 dots mean if you didn't know that, therefore the limit as x approaches 0 of the interior function must also equal 1, right? If this has a limit and this has a limit, this must have the same limit. So all 3 of these functions are headed toward y equals 1 from either side. And because the red fits between the blue and the green on both sides, and the inequalities remain. Now, if they cross over each other, like if the red gets bigger or smaller, like if it's not squeezed in between these 2 functions, then this theorem doesn't apply. So it's called the squeeze theorem for that reason. It's called the squeeze theorem because this f of x function is squeezed between 2 graphs. Okay, so in your lab, you're going to have to find functions that are either under or over a given function in order to evaluate a limit. And you're going to have to use Maple to do this. All right, so before we get into instantaneous velocity and derivatives, let me share with you JCC students. So this next little bit is just for my JCC students. In the Getting Started folder, if you go to the weekly assignments here, And by the time this video gets uploaded, it should be ready to roll for week 3. But in the getting started section, you might remember the first week having some information about this software package called Maple. You are required to use this because this is NC State's Calculus 1 class, and this is what NC State does with their students, so we have to teach this class the way they do. And Maple is a computer algebra system, and it's a really powerful piece of software for math. If you've ever used like Photomath or Mathway or Chegg or something, they don't even hold a candle to Maple. Maple can run circles around those things. So here's what you would do. You would click this link, right? And yep, I guess click the link below to open the page in a new window. Okay, so you would have to click that link and to download, right? So if you're a Linux user, you would download the Linux. I have a Mac, obviously you can see all these buttons at the bottom. So I've downloaded, this is the Maple icon, if you will. I've already downloaded mine and installed it, and there's one for Windows. Okay, so go download it, and then there is a code here for, this is just for my JCC students. If you happen to find this on YouTube, it ain't gonna work for you, sorry. So definitely download that, okay? And I'm going to close out some stuff and get started all over again because I've already done this stuff. Okay, so let me open up Maple all over again and start from scratch. And let me show you how I would do this whole squeeze theorem problem in Maple, okay? That's a little bit technical. So first thing I'm going to do is I'm going to create a new worksheet. I do not want to create a document. I'm going to create a worksheet. And if you hang on just a little bit, I'll show you how you can print this and submit it in Blackboard. You can save any of these to a PDF document. Okay. So you'll, first of all, this is a little overwhelming, right? You've got all of this wonderful stuff, matrices. There's Greek things. If you click over here with these little palettes, like you can put Greek letters, and you can put in matrices, and you have all this calculus stuff over here, and all this wonderful things, right? So the first thing I want to do is make this font really big so you guys can see it. Okay, hopefully you can see what that word says. It says hello at the top of the page. Tell you what, I'll make it a little bit bigger just in case. I got a really big monitor, and this is going to be reduced down to 360p here in a minute. Okay, so what I want to do is I want those three functions to appear, right? I want f colon equals, and as soon as I type f colon equals, it kind of comes over here and it says, hey, this is how you define a function in Maple, right? So my function is going to take f colon equals f of x. This is Maple's code syntax, if you will. Okay, and I want to assign that. I want to map f onto, by using a hyphen and a greater than sign. That makes an arrow. And what did I want? I wanted to make this the sine of x divided by x. Okay, so there's that. There's my f of x, right? And it's really small here. I wish the output would be a little bit bigger, but it's just telling you the same thing that you inputted. Okay, let me see if I can do all and make it really big, like 36. There we go. Now everything is nice and big. Okay, so I want to do g of x, g colon equals x, and that maps this function g onto, so this is hyphen greater than 1 minus x squared. Oops. Well, it just looks a little bit weird, but there we go. And I don't know why it won't make the output really big, but there you go. All right, and then h of x, how do I do that again? Colon equals x mapped onto, so that is hyphen greater than 1. Okay, and let me make that real big for everybody to see. Okay, so these are, I need to see these three functions defined in Maple. Okay, now the next thing you're going to have to do is plot this. So you're going to do plot, and if you don't know how to plot something, you can highlight that and you can get help on the command, and it'll pop up a new window that tells you all about the plot command. It'll tell you all the steps involved. Okay, so I'm going to show you how to plot all three of those on the screen. I'm going to do parentheses, and I want to do a left-hand bracket because I want to put all three of these on there. So I'm going to copy and paste these in there. I want F, G, and H, all three of them, to appear on a graph, right? Oops, sorry about that. Nope, I just wanted one. Son of a gun. There we go. All right. Now, if I do that and I close the parentheses, nothing's going to happen yet. Okay, so what I have to do is I have to put comma x. And if I do that, I'll get this nice looking graph in Maple. You have to use Maple to do this. I know I showed you Desmos earlier, but this is the Calculus 1 graduated software that we have to use, right? Now, you can see that it's defaulting from -2 pi to 2 pi. Remember, our interval was from -1 to 1. So I can just say x equals -1 dot dot 1. If you put dot dot, it's like an interval. And now you can see, okay, there's my h of x, there's my g of x, and this function f of x really is squeezed in the middle. So to answer questions in the lab, you need to find on your own, you can use Desmos to find these functions if you want, a lower bound function and an upper bound function that squeezes the graph between them, okay? And the one needs to stay all the way above except at the limit point. The other one needs to stay all the way up below except at the limit point. And f of x should be squeezed between these. And then you know, pause this video or rewind if you'd like to see how to type these in Maple. You might need to watch this a couple of times or put it on slow-mo, right, or that kind of thing. Now, in order to print this out, right, you can do the following. You can go up here and do File, Print. You can save this as a worksheet or workbook or document. You can save this in lots of different ways. You can export it as HTML or LaTeX or other things. This is for like mathematicians that do research, okay? But all you guys really need to do is just print it. And on my Mac, and it should be the same on Windows, you see where it says PDF down here? Just click on that and do Save as PDF, and it'll print it out as a PDF. Okay, so I'm going to say, you know, Lab 1.3 Maple, and I'm going to save this. Let's see, I want to save it to my downloads, and I can give it a title like my Squeeze THM, right? Something like that. All right, and then when I do that, down here it popped up that it's in the it's in my downloads, right? So there it is. Ta-da! Here it is. Here's my wonderful output with the huge text. Maybe yours, the text won't be that big. I made mine 36 points so everybody could see it in this video, but of course you don't need to make yours that big. Okay. So that's how to do an output file for this. You could, again, you could just print it to PDF. I would encourage you though to save your graph in case you need to go back to it and fix something before you're ready to print it out. You're gonna have to do 2 of these for this week's lab. Okay. All right. Now back to, let me minimize that. Back to our last part, right? The last part. So move my writing tools over here. Okay. There's this thing about, if you read in section 1.4 of your textbook, and also, by the way, 2.1 has really the same thing. There's some business about instantaneous velocity. And this is really getting into like the limit definition of the derivative. So what do I mean? Well, let's say that we have a position function. You might remember this from your Math 171 class, or from college algebra, or from an earlier class, that S of t, I don't know why that's still stuck there, S of t is a position function. Okay, so, and it's usually quadratic, right? So it's like, I don't know, -1/2 gt squared plus v0t plus s0, or something like that, right? Where g is the acceleration due to gravity on Earth, and this is initial velocity, and this is the initial position, right? So you may have seen that before in another math class. If not, no worries. But what we can do is we can do an average rate of change. Again, from a previous, average rate of change would be something like, you know, S2 minus S1 divided by a time interval, time 2 minus time 1. We call that an average rate of change. And if you remember last week's lab, you know, you had this graph, and then there's a parabola here, and there's a point, and then there's a point there, and a point there, and a point there, and you're finding the slope between these points, which is an average rate of change, and then the slope between these points, which is an average rate of change, and then the slope between these points, and eventually these two points get really close together, and it's just the slope of one point. And you've heard me talk about this before, right? So you can't just divide a single number by itself, right? Like the slope of a point by itself is kind of like, well, if you divide by the 0, you get nothing, right? So what we have to do is a limiting process. So the instantaneous velocity is not an average velocity. This happens at one point. And what's going on is, instead of you having a v of t function, instantaneous velocity, okay, what's happening is you will take a position at some later time, so let's say t plus something, we'll call it h, minus s at a previous time, original time, and we're going to divide that by a later time minus the original time. And when you do that, look what happens. The t's cancel out down here, right? T minus t, okay? And we know that these two positions, if you will, get closer and closer and closer together as h approaches 0. So what's happening with the instantaneous velocity is we're doing a limiting process. We're taking the limit of this quotient. We're taking the limit of this as h approaches 0. Okay, let me go rewrite that down there. And this is a disguised form of the derivative. And one way that you'll learn later on in this class that the velocity at time t is the derivative of the position function, and this is pronounced s prime of t. But this velocity function is really just the derivative. It's called the derivative, And it's this stuff inside here you might remember from a previous math class too. It's called the difference quotient. It's the quotient of two differences, right? So, and again, we've talked a lot about this in the past couple of videos, but that's what an instantaneous velocity is. And what we're going to have to do is use this limit to calculate something that we call a derivative, right? So here's a final example. I will leave you with this, and then I'll send you back to Maple before we leave, because Maple has a tutor in it. Did you know that? Yeah. So there's tutoring, by the way, in this place called the Academic Skills Center on JCC's campus. And where is this located, Mr. Molakash? It's located in the library, the Learning Resource Center. So if you do a real quick Google search, just Google Academic Skills Center, JCC campus, and you'll find their tutoring is available. They do virtual tutoring there. They do face-to-face tutoring. Of course, if you come on campus right now, you have to wear a mask. Their entire existence is so that you can be successful in your academic career at JCC. So definitely take advantage of the tutoring center if you've never been there. Set up an appointment, and you can, get the tutoring that you need if you can't meet with me. But there's tutors in Maple in your computer program. So we'll show you that in just a few minutes if you'll hang in there a little bit longer with me, okay? All right, so here's an example that we're going to do. We're going to find this thing called the derivative, okay? And we're going to use a function, f of x. Well, I'm hoping that works out. It doesn't like me. Let's try again. Maybe I have to write slower. I don't know what's going on. F of x equals, and this, what I want to use is 2x squared plus 3. 2x squared plus 3. Okay. Now, what I want to do is find the derivative. So the derivative, f prime of x, there we go. Now things are working out a little bit better. I didn't wear my fancy glove this week. Let me put that on. Maybe that's the issue. I think my fingers here are hitting the writing tablet, so maybe that was it. But anyway, yeah, the function's derivative is going to be the limit as h approaches 0 of f of x plus h minus f of x divided by h. So this is getting ready to be complicated, okay? I'm just not going to lie. It's going to be complicated. So get ready to do some work, okay? First of all, what I would do is I'm going to outline a couple of things. First off, this f of x is the same thing that is up here, right? Okay, so let's write down all this stuff all over again. There's an h on the bottom, and then this pink stuff is the original function that I was giving you, so 2x squared plus 3. All right, so the question is, what is this other thing? What is this other thing, right? What do I put in for that? Okay, well, I have to do a substitution, and instead of evaluating f at x, that x and that x are now going to be x plus h. So I have to do 2 times not x anymore, but x plus h. And that's what goes here, okay? 2 times x plus h squared plus 3. All right, so all that, subtract all that, okay? Now, right now, if I plug in h equals 0, I'm going to get 2x squared plus 3 minus 2x squared plus 3, which is 0, and divided by 0. So at this moment, I cannot evaluate this limit. Unfortunately, I have a lot of algebra to do. So we're going to do some algebra. That's why you took all those other classes before this one, right? So here we go. This is going to work out to be a long thing. So let me do the blue part first. The first thing I'm going to do is the FOIL method. So x plus h times x plus h turns out to be this. Now you may want to pause the video to convince yourself that x plus h times itself is equal to this if you do the box method or the FOIL method. Alright, plus 3. Now the next thing I'm going to get to do is distribute the minus sign here. You know, the great thing about videos is that if I'm going too fast, you can put it in slow-mo. Yes, you can. Alright. Next thing we're going to do is distribute this 2. So let's do all that. So this is going to be 2x squared. Oh, by the way, if I were to put in h equals 0, I get 2x squared plus 3 minus 2x squared minus 3. Oh, that's still 0 divided by 0. No bueno. Hang in there. There is an end in sight. I will show you. You gotta stick with me, okay? Calculus is not for the weak, not for the faint of heart. Okay, so all that, let's write everything else down in black, and now I'm not going to switch colors anymore. And you'll see why in a minute. Some wonderful things happen. Some wonderful things happen. Now, the reason I'm continuing is because even in this last step, if I put h equals 0, I get 0 divided by 0, right? But, big but, and I cannot lie. Watch this. Two x squared minus 2x squared is 0. I can cancel that out, right? I can combine like terms up here. 3 divided by 3 is also 0. And now what's happening is there's h's in the numerator, right? So I can factor in h out of what's left here in the numerator. I can factor in h out of this, and I can get what's left over is 4x plus 2h. Okay? Okay, now, even though this function that I'm trying to evaluate the limit of, this h equals 0 business, I get 0 divided by 0, but I can remove this discontinuity by canceling out the h's. I can remove that. And because I can do that, because h doesn't actually equal 0, it's very close to 0, I'm not doing 0 divided by 0, I'm doing a positive number divided by a positive number, or negative divided by negative. These are exactly the same everywhere except at 0, and h does not equal 0, so we're good, right? Okay, so now I can evaluate the limit. Now I can plug in the 0, right? And I get 4x plus 2 times 0, which is just 4x. Okay? Now 4x is the derivative of this function. Okay, so what we can write about this, let me write it over here. If f of x is 2x squared plus 3, then the derivative of that function is 4x. And the derivative is going to tell us lots of information. It tells us the slope of the tangent line at every x value. It tells us instantaneous velocity, instantaneous rate of change. It's just a wonderful, wonderful thing that we get to learn a whole lot about in Calculus 1. And when you move into Calculus 2, like derivatives are, you've already learned all of it, and you're just learning integrals at that point, right? All right, so this is the process. Go back and watch this again. Go through the steps, slow it down, okay? And reach out to me if you have questions, right? I'm definitely here. I can help you. You can go on campus to get tutoring. Now, last piece, okay? Speaking of tutoring, let me hide this and let me go to my Maple, okay? Back to Maple. And let me go up here to where it says Tools and Tutors. There are tutors for almost every class that you could possibly imagine, even pre-calculus. We didn't use Maple in pre-calculus at JCC, but all the stuff it can help you with, right? So for you guys in Calculus 1, you're learning calculus of a single variable. Multivariable calculus is Calculus 3, so you're not there yet. Vector calculus is also in Calculus 3. There's like lots of stuff here. So we're going to do calculus of a single variable, and we're going to do the derivative tutor. Derivatives. All right, and so up pops up a function in an interval, and it graphs this function, but it also graphs this other thing called its derivative, right? Okay, so here's what we're going to do. I'm going to input my function. What was it? X squared. No, 2x squared, my fault. 2x squared. It's a good thing I have notes over here, right? Plus 3. Okay. And let's see, I want to graph that from, I don't know, -5 to 5. That'll work. -5 to 5. And I'm going to hit display, and look, oh, it says, what does it say? The input value should be an algebraic expression in x. Did you notice that there's a multiplication sign down here when there's numbers? So what did I forget? I forgot to put a multiplication sign. That's probably going to happen to you too. The asterisk in Maple has to be used for multiplication, especially in these tutors. Okay, so hit display. Look at that. The derivative really is 4x. And as a nice little added bonus here, not only does it graph this original function, is this working out? Oh wow, it doesn't want me to, it doesn't allow me to write on this, so all I can do is type or whatever. Maybe I can write down here maybe. Oh well, it's kind of gone. Hey, there we go. Okay, so I'll have to use my mouse. For some reason my pen is dead. But this function right here is definitely graphed. It's a parabola, right? And the derivative of that parabola is this line. This line is the derivative, right? So let's say, at, I don't know, at x equals 4, if I wanted to find the slope of this tangent line, what I do is I put 4 into this, and the slope of that line is 16, because 4 times 4 is 16. So again, more of this is coming in the future, in future videos and future lessons, where we'll talk about how to find the slope of the tangent line using the derivative. There's even shortcuts to finding this derivative. So for example, like I knew if y was 2x squared plus 3, I already knew the derivative was 4x before even doing all that mess. Unfortunately, in your lab, in this week's lab, you're going to have to do the limit definition of the derivative. And here's the function you have to do it with. F of t is equal to 4t cubed plus 9. And, look, they want you to use Maple, right? It says go to tutors, not calculus 1, just, what does it say? Single variable calculus, and go to derivative to check your answer. But don't just write the answer down. You got to show all that wonderful work that I did earlier, right? You got to show all that wonderful work with all the limit as h approaches 0, blah, 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 blah. Okay, so there's a reason why there's only one of these here. Okay, there is questions on the intermediate value theorem this week. Let's see. Squeeze theorem that I talked about earlier, so that you have to squeeze these functions like I talked about earlier, and it wants you to use Maple. Give the functions you entered into Maple and plot them, print those plots out, and then continuity. So go back to last week's video if you need help with learning the definition of functions are continuous or not. All right, so I hope you guys have a great week. Hang in there. This is not going to get easier, but I am definitely on your side. I'm here to help. So, see you later.